Welcome to the video lecture series on digital image processing. Since our last lecture, we have started our discussion on a particular aspect of image processing techniques, that is, we are moving towards understanding the object present in an image, or we are going for interpretation or image interpretation. Now, to start with, we have said that if we are going for image interpretation or image understanding, basically recognition of the objects present in a scene, then the first operation that we have to do is we have to look for a proper representation mechanism of the object regions, and once we have a representation mechanism, then for that representation we have to find out a description of the object. Now, once we get a description of the object, then this description can be matched against similar such descriptions which are stored in the knowledge base in the computer, and to whichever such model or description our current description matches, we can say that the object present in the scene is that kind of object. So, it is an object X or object Y and so on. So, initially what we have done is, in our last lecture, we have discussed about a representation technique, about some representation techniques which are boundary based representation, and accordingly we have found out some description from this boundary representation. So, the first kind of boundary representation method that we have talked about is a chain code representation, and we have also seen that when we have a chain code representation, the chain code representation by itself is not scale independent or rotation independent, though it is translation independent. So, to take care of its dependency on the scale as well as its dependency on rotation, what we have done is we have resampled the boundary points by placing grids of different sizes. So, the different scales of a region can be taken care by placing grids of proper spacing, whereas to obtain the translation invariance, what we have said is, instead of taking the chain code itself, we can go for differential chain code. And we have said that we can obtain the differential chain code from the original chain code by considering that given two subsequent codes in the chain code, we have to find out that how many rotations one has to give either in the clockwise direction or in the clockwise direction to move to the second code from the first code. And if I represent this number of rotations that we have to give, the number of steps of rotation that we have to give in the form of a chain, that becomes a differential chain code. And finally, to make it rotation invariant, what we have said is, instead of considering that as a chain, we can consider this as a cycle, and in that cycle what we have to do is we have to redefine our starting point for chain code generation, so that from that starting point, if I open up that particular cycle, what I get is a numerical number. And we have said that this numerical number, if I follow a convention, that I will select a starting point such that the numerical number that is generated is minimum, then what I get is a chain code or differential chain code based description of the object shape or of the object boundary, which is a descriptor that can be translation, rotation and scale invariant. And this particular minimum number that we get, we have said this is what is called shape number for that particular object shape. Then we have discussed about another boundary based representation technique, which is the polygonal approximation of the boundary. So, we have discussed various techniques of polygonal approximation technique, how a given boundary can be represented by a polygon. Then we have talked about a particular description mechanism, that if we model the vertices or the corners at different vertices of the polygon in the form of an autoregressive model of say order k, in that case we can form a set of linear equations. After solving those set of linear equations, we can solve for the coefficients of that autoregression model. And this set of coefficients can also be used as a descriptor which represents that particular polygonal shape. And these coefficients can also be used for matching purpose. In today's lecture, what we will talk about is we will discuss about some more boundary based descriptors. One of the boundary based descriptor we will talk about is what is called a Fourier descriptor. We will also talk about another descriptor which is called boundary straightness, and the other kind of boundary descriptor that we will talk about is called a bending energy. Then, as we have said that all these boundary based descriptors, we have said that this essentially captures the shape information of the object region. Now, to capture the shape information of the object region, similar such information we can also get from the region, not only from the boundary. From the entire region we can also capture the shape information of that particular region. So, we will talk about some of the region based shape descriptors like eccentricity, elongatedness, rectangularity, compactness, moments, and some other descriptors, which are the shape descriptors that can be extracted from the entire region, not only from the boundary. So, let us first talk about this boundary based descriptor, which we said is the Fourier descriptor. So, let us see what is the Fourier descriptor. So, suppose you have an object boundary, say something like this. Now, obviously, I will have an image axis. So, image axes are given by x and y, and this boundary is nothing but a set of discrete points in this two dimensional x y space. So, what is this boundary? This boundary is actually a set of points, and let us represent the point, a particular point, by Sk. So, this boundary is nothing but a sequence of such points Sk in our discrete two dimensional space x y. So, this Sk in the two dimension will have a coordinate which is given by xk and yk. Now, if I assume this x axis to be a real axis and y axis to be the imaginary axis. So, what I am doing is I am interpreting the x axis as the real axis and y axis as the imaginary axis. Then every boundary point Sk in this sequence of boundary points can be represented by a complex number which is given by xk plus jyk, where j is equal to square root of minus 1. So, based on this interpretation that we are interpreting the x axis as the real axis and y axis as the imaginary axis, every point, every discrete point on the boundary can be represented by a complex number. So, if I take the sequence of such boundary points, when we trace the boundary either in the clockwise direction or in the clockwise direction, what we get is a sequence of complex number Sk. And suppose we have total of capital N number of points on this boundary. So, in this particular case, our k will vary from 0 to capital N minus 1. So, I have n number of complex numbers taken in a particular sequence which represents our boundary. Now, what we want to do is, we want to take the discrete Fourier transform DFT of this sequence of complex numbers Sk, where k varies from 0 to capital N minus 1. So, as we have noted earlier when we had talked about the discrete Fourier transform, you find that if I take discrete Fourier transform of this n number of sample points, in this particular case each of the sample points is a complex number, what I get is capital N number of coefficients, which are the Fourier coefficients. So, I can write that expression in this form, say AU is equal to 1 upon capital N, take the summation Sk e to the power minus j 2 pi by capital N uk, where k varies from 0 to capital N minus 1. So, by doing this, you find that I get capital N number of complex coefficients AU. So, each of the coefficient AU is complex. Now, this set of complex coefficients can be used as a descriptor which describes this particular given shape or this particular given boundary. Now, obviously, if I take the inverse discrete Fourier transform, the IDFT of this set of complex coefficients AU, then I should get back Sk, our original set of boundary points. So, this inverse discrete Fourier transform is given by AU e to the power j 2 pi uk by capital N. Now, u has to vary from 0 to capital N minus 1. So, this set of u, this capital N number of complex coefficients, this is what is known as Fourier descriptor of the boundary points. So, given a set of boundary points, we consider each of the boundary points as a complex number. By tracing the boundary in a particular order, either in the clockwise direction or in the clockwise anti-clockwise direction, I get a sequence of such complex numbers. I take the discrete Fourier transformation of that sequence, and the such DFT coefficients, the set of DFT coefficients, that become the Fourier descriptor which describes the given boundary. And naturally, if I take the inverse discrete Fourier transformation of these Fourier descriptors, then I get back our original boundary points. Now, in most of the cases, for representing in a shape, we normally do not consider all the capital N number of Fourier descriptors, that is all the coefficients in this Fourier descriptor. Rather, we consider say first capital M number of descriptors for describing the shape, where obviously this capital M is less than capital N. Now, using this capital M number of Fourier descriptors, if I try to reconstruct our original boundary by taking inverse discrete Fourier transformation, then because we are cutting out some of the Fourier descriptors, naturally our reconstruction will not be exact, but rather what we will get is an approximate reconstruction of our boundary points. So, that approximate reconstruction or approximate boundary points are given by Sk is equal to u a u e to the power j 2 pi u k by capital N, where now this summation will be for u equal to 0 to capital M minus 1. So, here you find that and k will vary from 0 to capital N minus 1. So, find that though we are taking less number of DFT coefficients or less number of Fourier descriptors for reconstruction of our original boundary points, the number of boundary points which are being reconstructed will remain the same. But what we will lose is, we will lose some details of the boundary. Say for example, if I have a set of boundary points which correspond to a square. So, if I consider very few number of coefficients, maybe say 1 or 2 discrete Fourier transformation coefficients. So, in that case our capital M will become 1 or 2. In that case, after taking this inverse Fourier discrete Fourier transformation, I will get capital N number of boundary points which is same as our original number of boundary points, but now the points will lie on a circular shape like this. So, I will get back this original shape if I consider all the capital N number of Fourier coefficients, the DFT coefficients for reconstructing the boundary by inverse discrete Fourier transformation. If I consider say very few number of discrete Fourier coefficients, say 2, then I will get a circular shape. If I increase it further, maybe say 10 or so on, I will get a shape something like this. So, in such case, you find that the details of the corners will be lost, but still I can maintain the basic essence, the primary essence of the shape of our original boundary, which was a square, and it becomes almost a square. So, by considering few number of DFT coefficients as Fourier descriptors to represent the boundary, I can approximately have a representation of the boundary, and this gives an approximate description of our boundary. So, this Fourier descriptors can be a very important descriptor which can be used for object recognition purpose. And obviously, if I have two different shapes which are widely different, then the Fourier descriptors for these two widely different shapes are going to be widely different. So, I can easily discriminate between the descriptors, between the shapes, between two or more shapes which are widely different. So, now let us take that what other boundary based descriptors that we can have. So, other boundary descriptors. So, another form of boundary descriptor is what is called boundary straightness. This boundary straightness is defined based on the concept of boundary curvature. So, as we know that in continuous case, the curvature at a point is given by rate of change of slope. So, if you take the derivative of the slope at a particular point, what you get is the curvature at that particular point. So, this boundary straightness, even in discrete case, it is defined as number of pixels, the ratio of the number of pixels where the boundary direction, the direction of boundary changes abruptly. To the total number of boundary points. So, you find that in our case, we are not going for exact measurement or exact calculation of the curvature at a particular point on the boundary. But what we are doing is, we are trying to find out, identify those points on the boundary where the direction of the boundary changes abruptly, because those are the points where the curvature is likely to be quite high. And I consider the number of points on the boundary where the direction of the boundary changes abruptly, and take the ratio of these number of points to the total number of boundary points. And this ratio is what is called the boundary straightness. So, you find that lesser the number, smaller the number is, that is boundary straightness, the boundary is going to be more and more linear, it is more straight. Whereas, if this value is higher, if this ratio is higher, that means there are more number of points on the boundary where the curvature is very high. So, we cannot say that the boundary is straight in such cases. So, this gives a measure of the straightness of the boundary. Now, the question is that how to find out that what are the pixels where the boundary changes abruptly. So, if I consider, say, these are the set of points, say these are the set of points which are on a boundary, and I take this ith pixel where I want to find out whether the boundary changes abruptly at this ith pixel or not. So, what I do is, I take a distance b and consider two more points, one at, say, I consider one point I plus b in one direction, and I consider another point I minus b in the opposite direction. Then what I do is, I draw a straight line passing through I and I plus b, and I draw a straight line passing through I minus b and I. And I try to find out that what is the angle between these two straight lines, say angle beta. So, you find that if the boundary changes abruptly at this pixel location I, then this value of this angle beta will be quite high. Whereas, if the boundary does not change abruptly at this location I, then the value of this angle beta will be very low. So, depending upon the value of this angle beta between these two line segments, one passing between I minus bth point and ith point, and the other one passing between ith point and I plus bth point, I can determine, I can estimate whether there is a sharp change of boundary direction at this ith pixel or not. So, this way I find out the number of pixels where the boundary changes abruptly, and the ratio of that such number of points to the total number of points gives me a measure what is called boundary straightness. The other form of boundary based descriptor can be what is called bending energy. So, what is this concept of bending energy? Bending energy is, suppose we have a steel rod and we want to bend that steel rod to a given shape. Now, while doing so, the amount of energy that we have to spend to bend the steel rod to a given shape, that is what is called bending energy. So, considering this, you find that if I want to bend the steel rod such that the curvature will be more, I have to spend more amount of energy. Whereas, if the shape has a curvature which is less, then I have to spend less amount of energy. So, this bending energy, this can be computed from the concept of curvature at different points on the boundary itself. So, at the kth point, if I say that C k is the curvature at point k, in that case the bending energy corresponding to that point is a square of this. So, the total bending energy of the boundary, this can be computed as, say, bending energy is equal to summation of C k square where Ck is the curvature at point K, and I have to take this sum for all the points lying on the boundary. So, this will be for k equal to 1 to say capital L, if capital L is the total number of boundary points, and I normalize this. So, I have to divide this measure by 1 by L. So, this becomes my normalized bending energy, and this normalized bending energy, or normally called bending energy, this is also a feature or a descriptor of the shape of the region. So, based on the boundary, and in a similar manner we can find out many other descriptors which represent the shape based on the boundary information itself. So, as the shape information, as we said earlier, that the shape information can be described from the boundary of the region, similar shape information can also be obtained from the region itself or the region area. So, let us see that what are such descriptors that we can obtain from the shape information that we can obtain from the region itself. So, now we will talk about region based shape descriptors. One of the obvious descriptor is the region area. Now, what is region area? Region area is nothing but the total number of pixels belonging to the area. Or belonging to the region. So, it is the total number of pixels belonging to that particular region. So, obviously, you find that this region area can be a descriptor which is translation invariant or rotation invariant, because if I translate the object or if I rotate the object, the total area or the total number of pixels within that object will remain the same. Whereas, the region area, this descriptor is obviously not scale independent, because if I zoom the object, the total number of pixels belonging to the region will be more, whereas if I zoom it out, in that case the total number of pixels belonging to that particular region will be less. So, this region area, though it is a feature, but this cannot be used for object description or object recognition. The other form of descriptor, which is called Euler number. Now, Euler number, it is a simple topological invariant. Now, what is Euler number? Suppose I have a region something like this, and within this region I have a number of holes. So, find that in this particular case I have one connected component of the region, and within this connected component I have a number of holes. So, in this particular case I have one connected component and there are 3 holes. So, the Euler number is defined like this. So, Euler number is equal to S minus n, where S is the total number of connected components of this particular region. So, S minus n, and n is the total number of holes in this region. So, in this particular case, because it has got only one connected region and 3 holes, so Euler number in this particular case will be equal to minus 2. Whereas, if I have an object of this form, say one connected region and one hole within this connected region, in this particular case the Euler number will be equal to 0. So, as I said that this Euler number is a topological invariant descriptor. Why it is invariant? Because if I zoom this particular region or zoom out this particular region, if I translate the object or if I rotate the object, the Euler number will remain the same. Obviously, the restriction is if I zoom it, in that case it should not be stretched so much that the single region gets breaks into two different regions, or the viewing angle should not be such that one of the holes is not visible, one or more of the holes is not visible. So, within that constraint you find that this Euler number gives a descriptor, a topological descriptor, which is invariant to rotation, translation and scaling. The other kind of descriptor which can be used, which is again a region based descriptor, that is horizontal and vertical projections. Now, what are these horizontal and vertical projections? Suppose I have some object region, something like this, and this is my x axis, horizontal axis, and this is the vertical axis y. So, what I do is I take the projection of this on my horizontal axis, this becomes the horizontal projection, and if you take the projection of this on the horizontal axis, the projection will become something like this. And I also take the projection of this area on the vertical axis. So, in this particular case, the projection on the vertical axis will become something like this. So, this horizontal axis, the horizontal projection, this I call PHI, and this can be computed by simple expression Fij, where j varies from, and this summation has to be done over this variable j. That means, I have to take the summation along a particular column. Similarly, this projection I call vertical projection. So, this is say PVI, which can be simply computed in a similar manner. It will be the summation Fij, where now this summation has to be taken over I. So, this should be PVJ. So, you find that depending upon the shape of this particular region, these two projections, that is the vertical projection and horizontal projection, they are going to be different. And normally these are used as descriptors in case of binary image. This is not normally used in case of gray level image. The other kind of region based descriptor that can be used, what is called eccentricity. Now, what is eccentricity? Suppose I have a region, say something like this. What I do is I find out a chord of this particular region of maximum length. So, suppose I have a chord this which is of maximum length, and I call this chord as chord A. And then I find out another chord of maximum length of the same region, which is perpendicular to the chord of maximum length. So, I call this chord as chord B, and my restriction is that these two chords have to be perpendicular to each other. So, given such a situation, then the ratio of the length of the maximum chord, so length of A to the length of B. So, the ratio of these two chords, one is a chord of maximum length and the second one is a second chord which is again of maximum length, but perpendicular to the first chord, and ratio of these two, this is what is called eccentricity of this particular shape. So, this eccentricity can also be used as one of the descriptors, one of the shape descriptors, and as you see that it is also a region based descriptor. Of course, a similar such descriptor I can also obtain from the boundary of the region. Another kind of descriptor that can be defined, shape based descriptor, which is called elongatedness. Now, to define elongatedness, we construct something called a region minimum bounding rectangle. Now, what is this? Suppose I have a shape, a region shape of this form. So, something like this, and what I do is I find out a rectangle, a bounding rectangle of this region which is of minimum size. So, maybe such a bounding rectangle can be of this form. So, I have a bounding rectangle like this. Now, in this particular case, this shape has not become a proper rectangle because the angles have to be 90 degree. So, I have a bounding rectangle like this, and this bounding rectangle have to be of minimum shape, minimum size. So, this is what is called minimum bounding rectangle. Now, once I have such a minimum bounding rectangle, suppose A is the length of the larger side of this bounding rectangle and B is the length of the smaller side of this bounding rectangle. And the elongatedness in such case is defined as the ratio of A to B. That is, the length of the larger side of the minimum bounding rectangle to the length of the smaller side of the minimum bounding rectangle. This is what is called the elongatedness of this particular shape. Now, you find that such a kind of elongatedness, I mean this simple definition of elongatedness is not valid if my region is a curved region. For example, if I have a region something like this, for this kind of region, the elongatedness measure cannot be simply defined by this ratio of A and B. So, in such cases, to define the elongatedness of this kind of region, what I have to take into consideration is what is the thickness of this elongated region along with the length of the elongated region. So, one of the measure of elongatedness, I mean one way of finding out the elongatedness for such curved region is like this. It is defined as, for such curved regions, as area by maximum thickness. Square. So, I find out what is the area of this curved region, I find out what is the maximum thickness, and area divided by maximum thickness square, this gives me a measure of elongatedness for such a curved region. And one of the way to find it out is you find out area divided by 2d square, where d is the number of erosion steps that is needed before this region erodes to a null set. So, this is the maximum erosion steps. So, I can define elongatedness for a curved region in this way, and this elongatedness is one of the descriptors which captures what is the region shape. Some other descriptors, some other region based descriptors can be, one of them can be say rectangularity. Rectangularity is the ratio of a region area and the area of a bounding rectangle having a particular direction, say k, which is maximum. Okay. So, I can define this rectangularity as the ratio of region area and the area of a bounding rectangle which is maximum. So, if I say that f k is the ratio of the region area to the area of a bounding rectangle having direction k, then the rectangularity will be defined as simply maximum k over f k. So, what we have said that this f k is the ratio of the region area to the area of a bounding rectangle having direction k, and the maximum of these ratios is what is called the rectangularity of that particular given shape, region shape. And here obviously you find that when I say that what is the direction or a bounding rectangle having a direction k, we have to define what is the direction of a bounding rectangle. The direction of a bounding rectangle is defined as the direction of the larger side of the bounding rectangle. So, what you have to do is, given a particular region, I find out bounding rectangles of various orientations, okay, and for each of these orientations, for each of the directions, I find out the ratio of the region area to the area of the bounding rectangle. And for different directions, whichever gives me the maximum ratio, that is what is defined as the rectangularity of that particular region. The other kind of descriptor that can be used is what is called compactness. And this compactness is defined as the ratio of area by perimeter square. So, what does it give? We know that a circle is maximally compact. So, this compactness for a circle we know that area is given by pi r square and the perimeter is given by 2 pi r, and if I take the square of this and then take the ratio, this simply becomes 1 upon 4 pi. So, the maximum value of the compactness is 1 upon 4 pi, and the minimum value of the compactness can be 0. Suppose I have a long, very long region whose thickness is very, very small. So, in such case, in the limiting case, what we are going to have is a perimeter, infinite perimeter, but 0 area. So, if I take the ratio in such case, that area by perimeter square, this gives me a value equal to 0. So, these are the two limiting values of this compactness. One is 1 upon 4 pi, which is the maximum, and this we get for a circular region. And as the region shape deviates from circularity, the compactness will be less and less, and in the limiting case, the minimum value of the compactness will be 0. So, these are some simple descriptors, the shape descriptors, which can be obtained from the region itself, not only from the boundary. Now, there are some more shape descriptors which are also obtained from the region, and those are called moments. Now, to compute these moments of a region, our interpretation is the gray level image that you get is a probability density that represents a normalized gray level image represents the probability density of a two-dimensional variable. Now, with this interpretation that a normalized gray level image tells us the distribution of a two-dimensional variable, we can find out some statistical properties of the gray level itself. And these statistical properties are what are nothing but moments. So, a moment of order say p plus q, moment of order p plus q is defined like this. We have m p q, which is given by x to the power p, y to the power q, f x y, where f x y is the normalized gray level image. Take the integral dx dy, and this integral has to be taken in the limit minus infinity to infinity over y and minus infinity to infinity over x. So, this is what is the definition of a moment of order p plus q for a normalized gray level image f x y. In discrete case, this expression is converted into m p q is equal to I to the power p j to the power q f I j. Take the double summation where j varies from minus infinity to infinity and I also varies from minus infinity to infinity. Obviously, for a finite image, this j I and j limits will be changing accordingly, and in this case I j is the location of a pixel in the image and f I j is the normalized gray level of that particular image. Now, you find that the moment as it is defined in this particular case, this moment is not translation invariant. So, to make the moment translation invariant, what we take is what is called a central moment. The central moment of order p plus q is defined like this. The central moment m p q mu p q is defined as x minus x c to the power p y minus y c to the power q f x y dx dy, and again you take the double integral in the limit minus infinity to infinity. So, this is what is called the normalized moment, and again in the discrete case this normalized moment will be expressed as mu p q is equal to I minus I c to the power p j minus j c to the power q f I j. Take the double summation over I and j. Now, this should be I minus x c and this should be j minus y c, where this x c is nothing but m 10 by m 00 and y c is nothing but m 01 by m 00. So, you find that this x c and y c, these two coordinates specify what it specifies is nothing but the centroid of the region. So, that is why it is called central moment, and once we have this central moment, this central moment becomes translation invariant. But you find that these moments are not rotation and scale invariant. So, people have tried to find out the rotation and scale invariants from these moments. So, there are 4 different moment invariants which have been suggested. So, 4 and those 4 moment invariants are defined like this. So, I 1 equal to mu 2 0 mu 0 2 minus mu 1 1 square upon mu 0 0 to the power 4. I 2 is given by mu 3 0 square mu 0 3 square minus 6 mu 3 0 mu 2 1 mu 1 2 mu 0 3 plus 4 mu 3 0 mu 1 2 square plus 4 mu 2 1 cube mu 0 3 minus 3 mu 2 1 square mu 1 2 square, this divided by mu 0 0 to the power 10. So, the third invariant is given by I 3 is equal to mu 2 0 to mu 2 1 mu 0 3 minus mu 1 2 square minus mu 1 1 into mu 0 3 into mu 3 0 minus mu 2 1 into mu 1 2 plus mu 0 2 into mu 3 0 into mu 1 2 minus mu 2 1 square, this whole thing divided by mu 0 0 to the power 7, and similarly there is another moment invariant which is I 4, and that has a very big expression like this. So, we are not going into the details of how these moment invariants are derived, but the details of this information, if any of you is interested, can be obtained from this particular reference. So, this reference gives the details of how these moment invariants are generated, how these 4 different moment invariants are generated from the moments, and these are rotation, translation and scale invariant. So, today what we have discussed is, we have discussed some of the boundary descriptors, some of the descriptors using the boundary, as well as some of the shape descriptors using the region itself, and these descriptors can be used for high level recognition purpose when we try to match these descriptors with similar such descriptors which are stored in the knowledge base. So, we stop our discussion here today. in our next class, we will discuss about some more region based descriptors. Now, today what we have discussed is the region based descriptor, but these region based descriptors does not take into account the reflectance properties such as color or texture of the surface. We will talk about other region based descriptors, say for example, texture descriptors in our next lecture. So, let us see some of the quiz questions based on today's lecture and as well as the lecture that we have given in our earlier class. So, the first question is, what is chain code? Second question, how can you make chain code based descriptor rotation invariant? Third question, what is principal eigenaxis? Fourth question, what is Fourier descriptor? Fifth question, explain how Fourier descriptors help in object recognition. Sixth question, how can you compute elongatedness for curved objects? Seventh question, what is compactness? What are its maximum and minimum values? And the last question, what does 0th order moment represent in binary images? Thank you.